Okay, let's start recording atmospheric and oceanic sciences. Outline, 3 main points. Atmospheric science, we'll talk about various gases around the various planets, and then we'll focus on Earth, planet Earth. Residence time of water in the atmosphere, and then in the ocean. We'll talk about atmospheric circulation and then the Coriolis force due to the rotation of Earth affects a lot of the weather. Then forecasting the weather. Oceanic science, ocean temperature, ocean currents, El Nino and La Nina. This is interesting. And then some satellites that monitor the weather and so on. So let's skip this one. So we said that the escape velocity of the various gases around the various planets, that's the velocity above which a gas would escape gravity, pull of the planet, or below which it would get retained. So this is the escape velocity for Earth, for example, 11 kilometers per second. The gas has to be beyond this speed to escape Earth. And then Jupiter is pretty high because Jupiter is pretty big. Pluto is very small because the planet is very small. Anyway, these are the various predictions based on this escape velocity. Various predictions for the various gases, like hydrogen, escapes Mars, but is retained in the Jupiter and so on. Like water escapes Mars as well, is retained on Earth. Carbon dioxide escapes the rocky planets and is retained in the big ones and so on. Okay. Carbon dioxide is retained around Mars. Okay. Information about atmospheres of the other planets measured, like Venus has mostly carbon dioxide with minor amounts of nitrogen. Mars has a thin layer of mostly carbon dioxide. Jupiter has helium and hydrogen. Uranus has mostly hydrogen. Methane gives it the blue color, and so on. Here we're showing the variation of the temperature with altitude, kilometers, going up. So we see that temperature decreases mostly, except at the mesosphere where there's a lot of ozone that produces heat, so the temperature decreases and then increases here, decreases here when you're going up, and then increases here. This is solar wind. It's heating up the top of the atmosphere. Okay, as the temperature, the pressure always decreases, like an exponential. Airplane at 11 kilometer altitude flies in an atmosphere with a fourth of the ground level pressure. Let's talk about residence time of water. So water enters the atmosphere through evaporation from the oceans and leaves it through precipitation, rain. The residence time is the average time that the water molecule remains in the atmosphere. So residence time, the atmosphere is equal to the total amount of water divided by the precipitation rate. So if you take a column going up in the atmosphere, doesn't matter its size, so you gather up all of the moisture in that column, there will be 2.5 centimeters worth of moisture, water. And then precipitation rate is about 1 meter per year, averaged over the whole globe, averaged over the whole year. That corresponds to 9 days. Residence time of water in the ocean, the same type of thing, but now the total amount of water is 5 kilometers. And 1 meter per year, so that's 5,000 years. So water stays 5,000 years in the ocean, evaporates, stays 9 days in the atmosphere before returning to the ocean. That's an average. Okay. Let's skip this one, and go on to energy balance in the atmosphere. So we know that solar radiation warms half of the globe, and then Earth is spinning. And warm the other half a little bit later, okay? So Earth absorbs energy from the sun and radiates heat in all directions. It's what is called the black body. Okay, so skip this one. So atmospheric circulation, we said that most of the sun, the hottest amount of sun energy hits the equator, then diffuses towards the poles. But here there's maximum heating, and here there's no heating. I mean, there's very little. So there's a deficit in radiation here, and there's a surplus here. So there will be gradients of temperature. Heating generates circulation in winds because of these gradients. Wind is produced when two atmospheric layers meet, like for example, a high temperature and a low temperature. These generates closed loop circulation cells. Okay, let's skip this one. Let's talk about Earth's rotation. Produces what is called the Coriolis force. Here I'm showing the Foucault pendulum. It swings back and forth, and then due to Earth rotation, it veers slightly, slowly, clockwise. Okay? So it hits those pins that fall. So you see these pins are falling with time, but slowly. It's swinging back and forth. This is at the Smithsonian. Okay, so let's explain the Coriolis force. If you take two children riding on a circular platform, which is spinning clockwise, they're the two kids. When one child tosses the ball to the other, this one doesn't catch it because he would have moved to the left by the time the ball gets to him. In other words, this one tosses the ball, but this one is spinning, so by the time the ball gets over here, this one would have moved, so he will miss it. So this kid looking at the ball, it looks to him as if the ball is veering to the right. Why? Because these two kids are what is called a moving frame. Okay? So a fixed observer, on the other hand, like somebody on top of the building watching these two kids play, he will see the ball go straight line. Okay? Straight trajectory. Okay. So this is the moving frame, and then on top of the building, the fixed frame. So the ball veers to the right because they're moving counterclockwise. All right. Let me say one more thing. Now you take these two kids, instead of playing on a platform like this, you take them to the very North Pole. Okay? And they're tossing the ball. Earth is moving underneath them counterclockwise, just like here. So if one kid tosses the ball, same thing happens. It looks like the ball is veering slightly to the right. Okay? So let's talk about weather map. This is called a high pressure formation. It's an anticyclone. This is a low pressure formation. It's a cyclone. Okay, so you see the pressure here in millibar, 1020 millibars, so 1 bar, 1 atmospheric pressure, 1024, and so on. So pressure goes up here, and pressure goes up towards the inside. Let's skip this one. And then we said that the high pressure is called an anticyclone. It's nice weather, clear sky, and so on. And cyclone rotates clockwise. Okay, so let's look at the pressure gradient force. It goes from a low pressure to a high pressure. Pressure gradient force goes from a high pressure isobar to a low pressure isobar. There it is. So just like the kid is throwing the ball. Here, this is the driving force. It's called the pressure gradient force. So the ball veers to the right. There you go. So clockwise. So the kid is moving counterclockwise. Imagine. That's Earth. And the veers to the right. All right. Let's look at the low pressure formation, referred to as a cyclone, is associated with overcast sky and rain. Cyclone rotates clockwise, counterclockwise. Here is counterclockwise, and here is counterclockwise. Okay, a hurricane is a tropical cyclone. Why? Because here veers to the right, and here veers to the right, but here, this is the pressure gradient force going outward, and here, this is the pressure gradient force going inward, because it's an L formation. A hurricane is a tropical cyclone. Hurricanes rotate counterclockwise in the northern hemisphere and the opposite in the southern hemispheres. Hurricanes cannot cross the equator. Why? Because at the equator, the Coriolis force is equal to 0. Okay? Skip this one. So, for predicting and forecasting the weather, so we see this anticyclone and cyclone. This is a warm front moving northeast. There it is. These are isobars, and this is a high pressure anticyclone, and so on. This is the weather. So isobaric weather contour maps are produced using weather balloon launches twice a day. They're produced by National Weather Service, which produces these maps. And they're taken by various organizations to forecast the weather. Okay? Skip this one. So, the weather station constantly takes meteorological data, transmits them. Doppler radar is used to observe the development of storm patterns. Okay? So, precipitation and seasons. This is a precipitation map of the United States. You see hot weather here, desert, and you see a lot of rain in California and down south, and in between for the Midwest states and so on. So we said that atmospheric circulation controls the weather. Oceans are deep and can store heat, while continental crust is thin. Its temperature varies widely. Big difference between day and night and so on, while the ocean is very, very stable. Temperature doesn't change much. This is the intertropical convergence zone. It's a line along the equator where there's maximum rain. Okay, so let's talk about ocean science now. Ocean temperature and salinity. Oceans occupy some 70% of Earth's surface. The top ocean surface temperature is around 25%. Forgot to mention that on the average, atmospheric temperature is 15%. Averaged over the whole globe, averaged over the whole year, the entire year. Okay. We said that temperature drops to 1 degree C at 5 kilometer depth. Those are the abyssal plains, the bottom of the ocean. When the surface temperature rises above 28 degrees C, that's when hurricanes form. We said that ocean salinity is around 3.5%. It's pretty stable, constant. Salts come from dissolved rocks on continents, process called weathering, that gets carried down rivers to oceans. Rain tends to dilute salt water close to river deltas. Okay, so remember we talked about the pressure gradient force. The ocean surface is equivalent force. It's called the Erkman force. Wind affecting the top of the ocean surface. We said three factors affect atmospheric effects on the ocean: heat exchange between the atmosphere and ocean, precipitation and evaporation, and the wind stress, the Erkman force. Okay, wind applies a force on ocean surface due to the Coriolis effect. Okay, so wind causes a surface current to the right of the wind stress. Remember Foucault pendulum, the H formation, they're all to the right of the force. Here also the wind stress force here and moves to the right. Okay, so this produces clockwise ocean currents. Let's look at them here. Skip this one, skip this one. There they are. The Gulf Stream, just like Foucault pendulum, just like the anticyclone, the H formation, there they are, the northern hemisphere. And it's opposite in southern hemisphere. Okay, the Labrador current, the Gulf Stream, this is due to Earth's rotation. Okay, they travel a few kilometers per hour. Okay, all right. So, summary: Foucault pendulum clockwise, the anticyclone clockwise, and the ocean currents clockwise. Okay? Then southern hemisphere is opposite. Okay? Remember that the L formation is opposite. So fish productivity in oceans. Light is absorbed in the upper 100 meters layer of the ocean. The rest of the ocean, 5 kilometers, remain dark. So fish lives in the top part only, where they feed on phytoplankton. Okay? Every organic matter that dies falls to the bottom. The bottom of the ocean, where there's no fish living, is rich in nutrients. Okay? While the top part, where there's a lot of fish, there's not a lot of nutrients. But there's mixing of ocean current up and down that favors fish productivity because it brings these nutrients to the top. Okay? This happens in equatorial and high altitude regions. So coastal regions where rivers flow mixes also the ocean surface. There's a lot of fish. All right. So let's look at La Nina, which is a normal state. Let's say that El Nino and La Nina are opposite states, ocean-atmosphere interaction. They alternate along the equatorial line in the Pacific Ocean. So La Nina is a normal state. There's plenty of fish. Why? Because there's this current we were talking about, brings nutrients from the bottom to the top. So this is an H state, high pressure, nice weather, no clouds. Everybody's happy, especially the fishermen off the coast of Peru. Plenty of fish. Now, El Nino, that current reverses. There's no more nutrients coming up. And this is not 20 degrees, but becomes 30 degrees. This is low pressure, a lot of clouds, a lot of rain, and so on. So this is El Nino. There's no current, there's no fish. Happens every 7 years or so. Felt worldwide. Monsoons in India, drought in Ethiopia, and so on. Year 2016 was a strong El Nino year. There's hardly any snow here in the United States. There were a lot of wildfires and so on. Anyway, ice and glaciers. Ice plays a major role in Earth's climate. Ice glaciers descend the mountain, carving the terrain. When they reach the ocean, they become icebergs. Most of the iceberg mass is submerged. What you see is barely 1/10 of the iceberg. So, permanent ice sheets in Greenland and Antarctica, the poles. Greenland ice sheet is 1 kilometer thick. It's been melting due to global warming. It's due to the burning of fossil fuels emits carbon dioxide, so that ice sheet, global warming ice sheet is melting. Okay, skip this one, and then let's skip these satellites, so on. Summary: planet Earth contains the right gases to sustain life. So far, this is the only known planet to sustain life. It has an atmosphere that shields it from dangerous solar radiation, presence of water in oceans, and much needed rain. The residence time of water is 5,000 years in the ocean and 90 is in the atmosphere. Earth's rotation, called the Coriolis force, and is tilted around its axis. So it produces seasons, drives atmospheric and ocean currents. Distribution of the sun's energy produces the weather. Events like El Nino are understood now, can be simulated, and there's weather satellites giving us a lot more information. Okay, thank you.